Math 152, Statistical Methods, Module 4, 8.3, Testing the Difference Between Means, Dependent Samples. So in this section, we will cover how to test a claim comparing parameters of two populations. And we're going to focus on dependent samples. So two samples are dependent when each member of one sample corresponds to a member of the other sample. And dependent samples are called paired samples or matched samples. So let's look at the difference between the two. So here we have independent samples where we have the sample 1, sample 2. And then we have dependent samples where we have the original sample that we took. We take those same samples again to see what the effect was. Okay? So for example, let's look at a sample. Sample 1 is triglyceride levels of 70 patients. Then sample 2 is triglyceride levels of the same 70 patients after using a triglyceride lowering drug for 6 months. Okay, so we're looking at the same 70 patients and we're looking at what happened to them after we introduced this thing into our environment. So let's talk about the t-test for the difference between the means. So the former two-sample hypothesis test with dependent samples, the difference between each data pair is first found by finding the difference between the entries. So the difference is x1 minus x2. This is the difference between the entries for a data pair. So we're going to subtract the two numbers. The test statistic is the mean, or I'm going to call it D bar, of these differences. So D bar, the D mean, is the mean of differences between paired data entries in the dependent samples. So we're going to take the sum of the differences and divide by n, which is our pair. These conditions are required to conduct the test, so we always check for these. The sample must be randomly selected. The samples must be dependent or paired, meaning it's the same sample we started with, we're going to end with. And both populations must be normally distributed, or the number n of pairs of data is at least 30. So n, remember, is not going to be how many individual data entries we have. It's going to be the actual pairs. Okay? And this should look familiar. This is our central limit theorem. Remember, we check to make sure it's random, and we also check to make sure that we have enough. If we don't have enough, meaning we'll have at least 30 samples, the population must be normally distributed. So if these conditions are met, then the sample distribution for the mean difference of D bar, the mean differences of the paired data entries in the dependent samples is approximated by a t distribution with n minus 1 degree of freedom. So our degree of freedom is n minus 1. And don't forget, n is the number of data pairs. So we're going to be using the t-test. Okay. Symbols used for the t-test for our dependent samples, our difference between means of our dependent samples. So we have n is a number of pairs of data. So I want to make sure you don't look at them as individual, look at them as a pairs. D is the difference between entries for a data pair. So to get that, we do x1 minus x2, and we'll see what that looks like in a minute. Our hypothesized mean Other differences of the comparative data in the population. So this is what the claim pretty much. Okay, look at it as a claim. And then D bar, the mean of the differences between the paired data entries and the dependent samples. And this is how we're going to calculate this. Sum of the differences divided by n. Remember, those are paired data sets. And then we have this symbol here, the standard deviation of the differences between the paired data entries and the dependent samples. So this is a square root of the sum of our difference minus our mean squared. Our difference minus our mean squared. So we're going to take our difference minus the mean, square it. I'm going to take all those, then divide by our degree of freedom. All right, let's get into the actual t-test for that we're using. So a t-test can be used to test a difference of two population means when these conditions are met. And we said that they are random, the samples are dependent, and the population is normally distributed, or n is greater than or equal to 30. Our test statistic is going to be the D bar, or our mean, the sum of our distances divided by n. Our standardized test statistic T is calculated D bar minus our hypothesized mean divided by our standard deviation divided by square root of n. That does look familiar. So standard deviation divided by square root of n. We've done that before. Your Excel or calculator will give you this. So you don't have to calculate it yourself unless you really want to. This will pop out when you run your test. Okay. All right. And the degree of freedom, just to remember, is going to be n minus 1. N minus 1. Here's our guidelines. You want to verify that the samples are random and dependent, and either population is normally distributed or n is greater than or equal to 30. So that's central limit theorem. State the claim. Identify HOHA. So remember, that's our HO and HA. Specify the level of significance. Identify the degree of freedom. Slow down a little bit. Determine the critical value T naught. Determine our rejection regions based on T naught. Remember when it's going to reject or fail to reject. Calculate our D bar or our mean and our standard deviation. Find the standardized test statistic and sketch the sampling distribution. So this is our T. And we sketch it or compare it to our T naught. Then we decide whether to reject HO or fail to reject HO and interpret the decision. We didn't talk about the p-value, but if you still want to use the p-value for this, you can, because the calculator and I believe Excel will also give you p-value. So if you're used to using p-value, you can still use that. So for the calculator, you're going to list your data in L1, the first set, the original data, and L2 is going to be your second, your dependent set, what happened after the fact. And then L3, we're going to subtract L1 minus L2. We'll practice that. Then we're going to run a t-test. In Excel, you're going to set up your L1 for your first data set, L2 for your second data set, And then we're going to do something a little different for Excel. We're going to subtract our columns. So column A minus column B, or whatever column you choose here. The columns are different in Excel. You get to choose, so you choose where you want to start. So whatever your first set of data minus the second set of data, you're still going to do that as well. And then we're going to do a third column for Excel, and we'll see that in a minute. Run a t-test. So stat t-test. Highlight your data, because we're going to have data. You're going to put our hypothesized mean here. We're going to talk about how do you get that mean in a minute. So you're going to enter the L3 in which the data is listed in your list. Okay, so we're going to run our L3, not our L1, but our L3. Keep frequency at 1. Highlight the HA inequality. Just like a regular test, you're going to have your TP value and your standard deviation. So let's look at our first example. I'm going to pause a little bit and let you put in your data into your Excel or your calculator. All right, hopefully you pause. If you haven't paused, go ahead and pause. All right, a golf instruction and club fitting company claims that the people who play golf can improve their average golf scores by taking lessons from one of their coaches. So we're looking at golf scores and then the golf scores improving. Okay. The average golf scores by eight randomly selected people who play golf are determined before and after taking lessons from one of the company's coaches. The results are shown in the table. At level significance 0.10, is there enough evidence to support the company's claim, assuming that average golf scores are normally distributed? So I'm looking and I see that they do have 8 as in, and this tells us that the golf scores are normally distributed. So we are good. We could do the problem. N equals 8 is not enough, but our golf scores are normally distributed, so we're good. All right, so hopefully you've put in I'm going to do the calculator on the left, Excel on the right. So L1, L2 is what you're putting in your calculator. For Excel, you get to choose. Some people like to label their columns in Excel, so I'm going to label this A. And if you didn't, it's fine. Just keep yours A and B. But then this is going to be B, and this is going to be C. So in Excel, you may want to label your persons and then put in for column B and C your data. For L3 or for column D, we want to label this as X1 minus X2. X1 minus X2. Sorry, had to pause for a student. So I have no idea where I stopped, but let me just do a quick recap. So we went over the problem, and we're stating that we're going to put in the calculator, L1 is going to be the first list, L2 is going to be the second list. In Excel, you may want to label your persons and then BC. And then in L3, we're going to put our X minus X1. So we're going to subtract these. And then in Excel, we're going to put it in column D. Okay, so I'm going to try to do this by switching the screens. Give me a minute.